design process for spider is just a matter of optimizing the transfer of load in the mesh as a restraining force that's applied to the block. So we have a restraining force P, and we want to optimize the angle and magnitude of that force, and we can do that with the spider design tool. So here's our block. It's held in place with some force P, and by placing the spider net around that block and anchoring it at certain points, we can optimize that restraining force and spread it out to the rock below. So we need to look at a few things, and we need to look at how a block could fail. And these are some generalized concepts here, but basically it's true, and it gives us a good idea into how the spider system works. First of all, that restraining force we talked about at P, we want to optimize that. We have the weight of the block that's acting downward. We have an angle between the horizontal and that force. And then we have an angle between the anchor and the horizontal. And we also have the angle that the block is sliding on, as well as the angle of the slope. So all of these factors play into our design. And finally, we have, and this is an important one, we have the angle between the mesh as it goes up over the block and goes down the block. So this included angle here is important on how the loads are imparted to the mesh. So let's look at this a little bit closer. Here's our block in 3 dimensions. Here's our restraining force P. Here's our block weight acting down. And we'll call this particular force in the mesh, we'll call it Z O, and we'll just use the word over. So that's Z over, that's the upward force in the mesh that's directed to holding the block up in place. And then there's a downward force pulling the block down and into the rock mass. And we'll call that ZU or Z under. So just for simplicity in English, we'll call those Z over and Z under. And then there's the angle omega. We discussed this already. That's the angle between the applied force and the horizontal. We want to optimize that angle and maximize that force. And then the angle of the anchors fits into this in relation to the horizontal. The angle of that sliding plane, we talked about that in the previous slide, and then the angle of the slope. And then finally this included angle, which is very important, and we'll see the effects of that. So let's look at that right now. So if we look at this included angle, how does that affect the force in the mesh? When we have an over force and an under force, and here is the included angle over here, theta. Here's our included angle, and here's the effect of that opening of the angle on the force in the mesh itself. So there's our under force and our over force, and this is for the over force here, the upward force. Notice as that angle opens up, increases, the force in the mesh gets greater. So as this angle opens up, as this mesh gets more parallel to the slope face, then the force in the mesh increases. All right, and let's look at a video of how this might work. Notice that the forces, as the block moves, the forces in both go down. We've got movement over here, and we've got forces on the bottom and the top. Here's force on the top, here's force on the bottom. With block movement, we have an increase in force, or decrease in force as it goes down, but the over force, the upper force, is always higher. And now the ratio of those two forces come into play. The upper force, the over force, is always higher than the lower force in the mesh, and so we give that, we'll call that a ratio eta. And so if eta is equal to 1, then our resultant, our restraining force, is the product of these two vectors. It always is, but it's equal. Both vectors are equal, therefore our restraining force is the product of this, or the square root of the squared terms. But if our force changes, in other words, if Z over gets greater than Z under, which is usually the case, then our eta is less than 1. So that is important in our calculation. So in this case, we have both of these equal. Eta is equal to 1. And in this case, we have the over force greater than the under force, which is typically the case. We'll never have the over force, the upper force, greater than the, or less than. Now let's look at another ratio. We'll call this one zeta. Zeta is the ratio of the lateral force to the upper force, the upward force in the mesh. So looking at this in plan view, looking down on our block, we've got a lateral force going sideways into the rock mass, lateral force here going sideways into the rock mass. There's an angle delta here, and the resultant of this lateral force also pushes the block in. And here's a rendition of it. Here's our force upward in the mesh, our force downward in the mesh, and here's this lateral force, which contributes to the stability of the mesh. The lateral force is equal to our ratio zeta times the force in the upward direction. And this is for simplicity, of course. So S is a function of the upper force. Now the design approach is limiting equilibrium. And in limiting equilibrium, we want to equate the restraining force to our forces in the mesh that are holding that block against the rock mass. So if we sum all the forces that are tending to drive